Hello, we're AUSense from Egypt. I'm presenting here on behalf of my team. Some of them couldn't come, but we're still very proud to be here. And today, this is our technical pitch. So the idea was we really wanted to do something that's outside of the box because once we found out that we had to get a signal in under 5 minutes, we really wanted to do something that was quite different and would actually work in under 5 minutes. So we wanted to work with electrochemistry. Through extensive research, what we found was this idea of redox cycling and detection by blocking. I'll explain in a second how this works. Okay, basically we have a screen-printed electrode. It consists of 3 electrodes. Firstly, we have the working electrode, which is basically our main concern and what we're actually changing in this biosensor, what we're mainly working with. I'll explain in a minute. We have the counter electrode and a reference electrode of silver chloride. So now I'm going to zoom in on the working electrode and how we have fabricated it, basically. Basically, it's composed of carbon, and then we add gold nanoparticles onto it. Then we add a self-assembly monolayer, which is basically a bridging group between the gold nanoparticles and the TNF that we attach later. This is a photo of the TNF immobilized. And then after that, we add ruthenium hexamine. Ruthenium hexamine is basically a redox cycling agent. Once we add it, what happens is current is produced because we apply a voltage, and electrons basically reduce the ruthenium 3+ hexamine to 2+. And then it cycles again as it's oxidized again. And this cycling keeps going on, thereby producing a current. Once we add the Humira, this cycling reduces because the electrons find it more difficult to reach the ruthenium hexamine, and basically this entire cycling reduces and the current therefore reduces. The other thing is once we add more Humira, the cycling further reduces. So what we did is we correlated the concentration of Humira with the current that is produced. We did that using chrono and parametry. The self-assembly monolayer that we chose is called 11-mercaptoendocanoic acid. Firstly, we needed to link between gold and the TNF. So on one side, we needed a thiol group, as you can see on the right. And on the left, we needed an OH group basically to bind with all the amines of the TNF. We also wanted to use a relatively large molecule in order to ensure that this large TNF actually binds strongly. And we chose to do covalent binding to ensure strong binding. This is our TNF alpha immobilization. The reason we chose TNF is because we needed something that was quite selective to Humira, and that's what we thought of. Through continuous research and testing and so on, we found that the optimum concentration of immobilization was 100 nanograms. To ensure actually that the TNF was immobilized, what we did was an SEM and an SEM imaging and an EDS analysis. As you can see in the top, this is the first image without immobilization before. This is after. This is after immobilization of TNF, and we can find that TNF is actually present, as indicated also by the increase in the nitrogen concentration and percentage abundance, I guess. So why did we choose the redox reagent hexamine ruthenium 3-chloride? The reason is, firstly, it's a very safe compound. We could have used other things. However, they're not the most safe, and they could pose some environmental hazards and so on. Also, it had a suitable reduction potential of negative 0.12. So this is quite far from the interferences that would occur at lower reduction potentials, which would cause a lot of interferences from the organic material, which is present in blood plasma and so on. It's also very stable. We tried to use ferricyanide, but we realized that it was depleting the gold nano layers that we had, so we couldn't use that. Also, we did the cyclic voltammetry, which indicated that this reagent is quickly regenerated, and therefore kinetically it's very good. And therefore, it also works in under 3 minutes. These are some of our chrono and parametric results. Basically, as the concentration of Humira increases, we find less current produced as a magnitude, ignoring the negative sign. The device that actually measures what we're doing is the MSTAT Pico development kit, which we bought from PalmSense. What we did was we 3D printed a package for it, and it's very small. It's 9 centimeters by 7 by 3, so that's easily portable and very easy to handle at home. We added a 12 microliter sample of blood alongside 18 microliters of the Redox reagent. Using a Bluetooth linker, or if you you can also use the cable. We can link it to either an Android phone or Windows. And it works in 3 minutes. We get stable current. Okay, our results were in 3 minutes, and they're high sensitivity, user-friendly, as well as wireless results. And it's a handheld device, as I previously explained. Thank you.
Thank you for your presentation. Are there any questions? Yes.
Okay, so
Hi.
congratulations for your work. What I find I think most interesting is the simplicity of the system, and typically this results in most or the highest probability of working. I have a couple of questions. So how reproducible is this immobilization procedure? Have you tested it? And how it impacts on your results?
Can I answer one question after the other so I don't forget? Okay, so the reproducibility. That word. Basically, what we did is in the beginning, we were trying this testing and so on, and we found that it was not reproducible. So we didn't understand what was happening. And then we realized that we can't reuse the same electrodes over and over, because we thought after a while that probably the layers are getting somehow depleted or they're getting washed off and so on, so we cannot reuse them. And so what we did was we used these electrodes one time, and they were very reproducible. So for example, just an hour or 2 hours ago, we were doing the 0.5 micrograms per milliliter, and the difference between the current that was produced was in the 0.002 microamps.
Yeah.
So it's quite reproducible.
So what would you say that is novel in your approach? Is the usage of the ruthenium compound? Because your colleague mentioned in a 1-minute pitch that you have a patent.
Yeah, I forgot
submitted.
to say that.
So
We do have a patent.
what is that about?
Basically, our
general
patent
terms.
is about the fact that we did this device and it works in under 3 minutes, and it's accurate, and at the same time, it's using a novel way, and it's applying it to TNF.
Yeah.
So, and it's also very user friendly, and it has a good application in real life and so on. And I guess the reagents that we used are purely things that we chose to use through research from so many different articles. We found that the best ones to use, such as the SAM, we chose this one, and then hexamine, we chose this one, so it was mainly our choices.
Yeah, okay. Thank you.
Thank you.
Thank you, and thank you for a nice talk. So do I understand you correct? You buy the electrodes from PalmSense, and the electronics is bought from PalmSense?
No, the electrodes are from Orion. We bought them with gold nanoparticles, and we didn't have a chance to actually create the self-assembly monolayer in our labs, because we were kind of running out of time, because chemicals could often take 2-3 months to arrive, and we didn't have the 11 mercaptoendocanoic acid in our labs. So we asked them, could you possibly customize a huge bulk? And they said yes, and that's where we bought the electrodes from.
Okay, so Orion was doing
Orion,
the surface modification. And so The novelty here is the new chemistry you did with the recycling.
I guess the chemistry and also the idea that we're using chrono and parametry with biosensors.
But that's
I think the idea of the reduction in current is quite. It wasn't something that we found straight away. I guess
a few people did that last year, even in this competition. But it's a good and nice and fast way to do things. Another question is that the assay time and the storage of your device, of your actually chip. So you preload the recognition elements on the surface of your chip. How long can you store the chip? How stable is it and robust?
Well, basically what we did is we had these electrodes, the self-assembly monolayer for about 2 months, and they were stable, they were fine. And then once we add at room temperature.
Oh, excellent, yeah.
And then we also, once we added the TNF, we didn't actually check how stable it was, but what we did is we left it for sometimes a week, 2, and it still worked.
Oh, excellent. So it has a good storage time. And that was also at room temperature?
Yeah, all at room temperature.
So you don't need to do any preloading or sample handling before you do your measurements?
No, we do. So the sampling handling, what we do is we mix 12 microliters of the sample with 18 microliters of hexamin ruthenium. And that's one of the drawbacks of our biosensor that we actually know of, because we can't ask consumers to actually dilute it. That's not an option. But what we do want to do in the future after, because we got the patent, we want to create membranes where we immobilize the ruthenium onto the membranes such that once we add the sample, on its own it will start moving and there's no need for dilution.
Okay, nice.
Thank you.
Thank you very much. Very interesting presentation, interesting concept. Indeed, like the previous person said, it's very simple and in that sense also very creative. I was wondering, have you tested the specificity to adalimumab? Because if you make a monolayer but you get a-specific binding of other proteins to your TNF-alpha, you get signal while patients don't have adalimumab. So how much testing have you done to...
Do you mean like a blank sample?
Yeah,
we
exactly.
did test with blank samples. That was actually one of the first things that we did to ensure that the TNF was actually immobilized. We tested with the TNF, and then we added the Humira sample. And when we saw that there was a reduction, it indicated that Humira actually attached to the TNF.
Yeah, this I believe, but there are patients that have high protein levels, patients that use other monoclonal antibodies. I was wondering, or patients with low albumin levels, do those factors influence your signal?
Well, what we did was we actually used blood plasma always, but we did not know the levels of these proteins in the blood. So we don't know if it would interfere.
Okay, that's unknown at the moment. Okay.
Yeah.
Okay.
But we use different blood samples quite often.
Yeah.
We were always using new blood samples because when we don't use fresh blood samples, our results were not accurate at all.
Yeah. Okay. Yeah.
A very quick last question.
Thank you. Very nice presentation and very nice idea.
Thank you.
I'm not very familiar with the redox cycling mechanism, so I hope the question doesn't come across as too dumb. Is it accurate in the entire range of antibody concentration, from very, very low, like the very, very low end of the spectrum, to the very, very high? As I was reading about it, I would imagine that in the away from the middle range, may have fluctuations or inaccuracies?
You mean like at very low ranges and very high ranges?
Yeah.
Okay, so what we did, the first thing that we did is we wanted to ensure that the range that was given in the competition actually worked. So we had to try at 0.5 and 10, and it did work. But we don't know if there are other ranges within Humira. We're not sure if it will work beyond that because we haven't tested that. But we know that it works within this range.
Within the range it was accurate, low concentration.
And also, if it did not work within this range, we basically change the concentration of the TNF. We can alter it. The TNF that is immobilized, we can alter it and play around with this to make sure that it fits.